Hey grade 11s, welcome back for another one of my solution set videos. I made this one a little bit differently. I've already solved all of the problems on my tablet and I'm just going to scroll through them and talk about them with you. I thought that might be a quicker way to make the recording and a quicker way for you to watch the solutions. I'm not sure if you'll appreciate that or if you'd actually prefer that I would continue the way I did it in the past where you'd actually see me solving the problems. There might be a little bit more insight to be had that way. So why don't you watch this video? And then I'd love to hear which way you prefer me to make the future solutions. If you'd rather me just kind of reveal solutions that I've pre-solved, or if you'd actually like me to have the recording of me solving the problems. I'm fine either way, so let me know what you prefer. Okay, getting into this. Problem number one begins a series of questions involving the same basic roller coaster setup. There's a figure that I'll scroll through right away. Part A basically says, if you have the roller coaster at point A, as shown, and it's moving already at 5 meters per second right here. The question is, what is that maximum height that it could have for the second hill, which takes it up to point C? So that's what we're asked to find, the maximum height of point C. Now, just to be clear about the physics here, this is very much a roller coaster. A lot of people don't stop to think about how literal that word coaster is in roller coaster. This little cart here is not powered. It doesn't have an engine. There's nothing pushing or pulling it. At some point earlier in the ride, not seen in the diagram, there was something that gave it energy. Usually on a roller coaster, there's a mechanism that kind of pulls the car up to the point, basically at a very, very high point, and then it basically releases it for it to just kind of coast through the rest of the ride. So to be clear, this thing is unpowered. So there is very much a maximum height that it could reach because the only way it could get there is by utilizing the energy it already has given to it earlier in the ride. So to solve this problem, what I'm recognizing is to just barely make it up to the top of the second hill, I can say that the velocity, or really the speed at point C, is effectively zero. I'm thinking of that case of just barely making it, effectively stopping here, but hopefully just enough to continue on with the ride, again, not shown. So that's how I'm going to solve this. The speed here I'm designating to be 0, because if it was anything greater than 0, then it could have made it even higher. So that's the basic setup of part A. So what is the height of point C? We know the speed at A, we know the height at A. So basic conservation of energy, the mechanical energy it ends up with at point C is equal to the mechanical energy at point A, allowing for the possibility that work was done along the way, but there was no work done along the way from point A to point C because, like I said, it's not powered. The only forces are the force of gravity, which are, the force of gravity is excluded from this non-conservative part, and the normal force from the track itself, which, as I believe I discussed in the previous solution set, would be perpendicular to the motion at all points. So the normal force is present, but not doing work because its beta angle would be 90 degrees throughout. Okay, so I can expand this. Mechanical energy point C is the kinetic energy plus the potential energy, the same thing for point A. There was no net work done by non-conservative forces, and there is no kinetic energy at point C by virtue of that premise of it being stationary when it just barely gets there. I should also mention that I've switched away from my prime notation. I just thought that throughout this solution set, because there are so many points A, B, C, and later on there's a point D and an E, I thought I would just use subscripts here. So flexibility with your notation is useful. If there's really only 2 points of interest, I like to use my prime notation. If there's several points, well, then I have to kind of go back to my subscripts to keep track of them all. Okay, so with that said, the gravitational potential energy point C is just mgh. Kinetic energy is half mv squared. Potential energy again is mgh. The mass is not known to us. We don't need to know it, so it just drops out. Do the algebra, solving this for the height at point C. I basically just rearranged it, and then I put the numbers in and got a numeric answer. So 6.28 meters is the answer to question A, or part A, number 1A. Okay, question B said, how fast is the car moving at the bottom of point B if it's moving at 5 meters per second at point A? So same starting conditions, but we're now more interested in point B. So really, question B is very much a repeat of the same basic physics here. Just we're now interested in point B. So again, conservation of energy, comparing B to A, still no work being done. the kinetic energy at B equal to potential energy at, kinetic at B plus the potential at B equal to the sum at A. Expanding each of those terms, m drops out again. Solve for the speed at point B to be 11.1 meters per second. So hopefully by now we're okay with this algebra and kind of number crunching part. I'll gloss over that for today. Okay, moving on to number 2. Same diagram, the same basic setup. We're now considering if point C is a given height, so it's a different configuration than before. If it's 15 meters, then what is the speed when it's at point C? So really this is yet another repeat of the same basic type of problem we just did. I'll just kind of scroll through it. I'll show you one thing that I did. No, it's coming up. I wrote it up a little bit differently in a solution that's coming up. So this really is just repeat to find the speed at point C. And then question B is how fast was it traveling at point A? Now, of course, we were given information about point B, so we're kind of working backwards to point A now. So to do that, I'm definitely keeping track of the mechanical energy at a later point is equal to the mechanical energy at an earlier point plus the work that was done along the way. I want to emphasize the order here because if this had not been 0, the order very, very much would have mattered. It's always the mechanical energy at a later stage equal to the mechanical energy at an earlier stage plus the work that was done along the way. Okay, but like I said, it drops out here, so it wasn't quite so critical, but good to have these things to be aware of. Okay, so once we're there, it really becomes a duplicate sort of question. So work ahead, find the answer to be 17.4 meters per second. And that's it for B. Number 3. A roller coaster given mass clears hill C, traveling at 3 meters per second. Okay, this one's a bit of a departure because we are told something very different here. If the roller coaster shown was traveling at 10 meters per second at the start, point A, and this is the new part. And let me just kind of grab this here. The car loses 10% of its initial energy before making it over to C. A is what's the height, and B, how much energy is lost to friction. So when you see statements like this, the car loses 10% of the initial energy, it's really important that you be able to translate this word-based sentence into a symbol-based equation. So I'll show you the way I did that. There's more than one way you could do it, but the way that occurred to me is to write it this way. I basically said, well, if you lose 10%, then you end up with 90%, and of course you can write 90% as 0.9, of what you started with. So I'd like to point out that that equation there is the mathematical representation of this sentence here. So you lose 10%, that means you end up with 90% of what you started with. So the mechanical energy at point C is equal to 0.9 times the mechanical energy at A. Now this equation itself is how I'm going to solve part A. I'm not going to roll into some kind of usual routine of mechanical energy at point C is equal to mechanical energy at point A plus the net work done along the way. I don't really need to do that because I have very, very specific information for this scenario, this custom equation based on this custom information, pertinent to this question. Okay, so let me just kind of undo that highlighting there. There we go. So building directly off of that equation, here's the mechanical energy at point C. It's the kinetic energy at C plus the potential energy at C, and that's equal to 0.9 of, and notice my brackets here. It's not just 90% of the kinetic energy, it's 90% of that total energy. So these brackets are important. But from there, the math should be very familiar looking, with the exception of this kind of new 0.9. Nonetheless, the math does what it needs to do all the way through to a numeric answer. And if you're a little unsure of that math, I'd encourage you to hit pause on the video and work your way through it. Hopefully you'll reach a point of saying, oh yeah, that makes perfect sense. If you're not making sense of that, then realize that you have a math concern, not so much a physics concern if you're understanding what I'm saying, but if you're lost in the math, then try to get that addressed. Ask your teacher, Mr. Dawson, or myself, what's going on here, and we should be able to lend you a hand. In particular, for example, So I know some students would be tempted to cancel off those g's there because you see one on top and one on the bottom, but for the record, no, those g's do not cancel. That would violate order of operations. So it was not an option here. I had to keep those g's in the equation. Okay, so moving on to part B, asked us, well, how much energy was lost in getting from point A to point C? So we know that we lost 10% of what we started with. So 10%, 0.1 of the mechanical energy we started with at point A. And of course, the mechanical energy at point A is just the kinetic plus the potential energy. So at this point, it just becomes a math routine, ultimately to find an answer of 1,390 joules. By the way, just a reminder, I round my answers off to 3 significant figures. So if you punch that into your calculator and you get something slightly different than what I write down here, that's okay. I'm only recording figures, recording answers to 3 significant figures. So if yours rounds off to mine, that's a very good sign that we really agree with each other. I'm just rounding it off. Okay, moving on to number 4. A new roller coaster has been developed. It's shown in figure 2, which is coming up right away. I'll get it on there. The track between A and C is frictionless. Now, up until now, we have been assuming an idealized condition. We've been assuming that the roller coaster is moving along with perfect conservation of energy. In other words, we've been assuming no air resistance or track friction or anything like that when we did our earlier calculation, especially in questions 1 to 2, I should say, because number 3 explicitly brought up an energy loss. So this one here is, however, calling out a section of track. Between C and D only, there is the introduction of friction. So friction is very much capable of doing work, and we're going to see that happening, I think, not until the next question that we explore that aspect, but it's very much coming. Nonetheless, from point A to point C is still idealized. The only force that's acting is the force normal, which we talked about, 90 degrees doesn't do work, and the force of gravity, which is a special conservative force not addressed with in the work part of the equation. So part A, listing off the information given, the height and speed at A is known. I added a point C just for clarification here because part A is asking us at that bottom of the first till. Now that wasn't labeled in the original diagram, so I just slipped in. We already had an A through D, so I know it's out of order, but I'll just call that point E. So the mechanical energy at E equal to mechanical energy at A plus, allowing for the possibility, but there wasn't any this time. And you know the drill from here. It's very, very straightforward. Part B says how fast was it moving at point B? So again, repetition. The repetition here is really for your benefit, just trying to get you down to this understanding. Although try to avoid falling into the trap of not thinking about it. Even if you're doing essentially the same problem, think about every single step that you're doing until you thoroughly understand it. Because if you're just saying, oh yeah, I know the routine, m prime equals m plus, and you're kind of just doing it almost from memory, that will not help you when the problems change. When there's a little bit of a twist, something a little bit different, and all of a sudden your memorized routine is not applicable. So even when there is some repetition, understand what you're doing and why you're doing it. So in part B, yes, it's true. It's in effect a repeat, but every step along the way should make perfect sense. So calling out the speed at point B equal to this expression, oh yeah, this is what I was thinking of earlier. I couldn't remember where I did this. I chose to make just a slight mathematical convenience for myself here. You can see in this step here, 0.5 mvb squared equal to mgha minus mghb. The m's have dropped out. Notice, however, that one way I can solve this for the speed at point B is by multiplying both sides of the equation by 2. So I clear this 0.5 by multiplying the left side by 2. That's why there's no 0.5 here. I've also square rooted, but let's just focus on the 0.5 for a second. Multiplying the right side by 2 requires that I put it in front of the GHA, so it's right there, and also in front of the other term, right here, 2 GHB. And the reason I'm stressing this here is because I tried to simplify this by factoring out the 2 and also the G, since both terms have a 2 and a G. I just thought that would tidy it up, especially since I'm going to be using this expression again in a subsequent question. So just to explain how I went from here to here, the 2G has been factored out. I also changed color here just for emphasis with how I'm going to reuse this coming up very soon. Right now, you can ignore the coloring. It doesn't really signify anything right now of importance. Okay, putting the numbers in, speed at b equal to, putting the numbers in, getting an answer of 29.7. Okay, now, when we go back to question C, just to be clear here, C and B are the same question, just with different points of interest. So question B referred to point B, question C refers to point C, but both points are in the same kind of physical condition. Starting from A, there was no friction at any point along this way up to point C. So there's no new anything happening here. So in this case, I couldn't resist myself. I said, you know what? If the speed at B, and this is where the coloring comes in, if the speed at B is equal to this expression, then honestly, the speed at C is going to be found in the exact same way. So there's that green kind of repetition here. I've only changed the subscripts B into the subscripts of C. So putting in my updated values there, get me an updated answer. And I did say I record answers to 3 significant figures. Peeking ahead a little bit, we're going to be using this number again in a later question. Whenever I reuse a calculated value, I like to keep a couple of extra sig figs in the subsequent calculations. So I'm going to call this my final answer for C, for question C, but I'm going to use this value coming up soon. Okay, moving on. Question number 5 says, after point C, there's friction to stop the cart moving at point D. Question A is how much work is done by friction to stop the car. All right, so just to go back to the diagram because I didn't paste it in again. The cart basically the cart has arrived at point C with that speed that we just calculated. It then slows down due to friction. I'm thinking maybe the brakes have been applied or something like that. And it ultimately comes to a stop at point D. Of real big importance here is to note that the height of point C is 80 meters, but so is the height at point D. The track itself was level between point C and D. It didn't go uphill, it didn't go downhill. Okay, let me return to where I just was. Yeah, so part A, how much work was done by friction to stop the car? And then we're also asked to find for that coefficient of friction. Okay, so moving in here, I'm now comparing point D to point C. Point D has mechanical energy, and it better be equal to the mechanical energy of point C plus the network that was done along the way by non-conservative forces from point C to point D. Now, the reason I was calling that out before is there is very much friction doing work here. So I can justifiably cross out the kinetic energy at point D because it stops at point D. And here's a kind of a clever little shortcut here. The gravitational potential energy at D is not equal to 0, but it is equal to the gravitational potential energy at point C, since they have the same height. So don't think of this as crossing out because it's equal to 0. Think of this as crossing out because this and this are equal, so I can actually subtract them from both sides of the equation. Okay, so that gives me nothing left over on the left side of the equation, and what remains on the right side is kinetic energy at C plus the work done by friction. That means that the work done by friction is the negative of the kinetic energy it had at point C. And that makes sense because however much kinetic energy it had at point C, friction is ultimately going to remove that energy. So let's just hypothetically say it had, just for argument's sake, say 25 joules of kinetic energy at point C. To stop it, friction would have to do negative 25 joules of work, effectively removing the 25 joules of kinetic energy. So let's find the real value because 25 was just a hypothetical. So the work done by friction is the negative of the kinetic energy at point C. So negative 1/2 mv squared, that's that speed value that I had from the previous question, kept to 5 significant figures. Putting the values in to get an answer of this, which I'm actually going to I'm going to use this value in a subsequent step, but I'll record this as my final answer to 3 significant figures. So the work done by friction to 3 sig figs is negative 70,600 joules. The last question on this worksheet is to find the coefficient of friction. So we can lapse back to some previous physics that we haven't been using as much lately, but I'm imagining this cart to be moving along on the track. Vertically, there's a force of gravity and a normal force. And yes, in this particular case, the acceleration being 0, the net force being 0 in the vertical, means that the normal force will be equal to the force of gravity, mg. Students in my class know that I always harp on this, that students often make the mistake of claiming the normal force is equal to mg when it's not applicable. So to be clear, in this particular case, yes, it is. It actually is applicable. The normal force does balance the force of gravity in this case, since there's nothing else vertically happening and it's not accelerating vertically. There is a force of friction horizontal though, and that's the reason the cart is moving to the right, but slowing down in the process. Friction is slowing it down. Now, if you wanted to find the coefficient of friction, you actually could go back to our earlier unit and use nothing but that physics. You could use Newton's second law to, you could use some kinematics to find the acceleration. You could then use Newton's second law to find the force of friction, and then find the coefficient of friction from that. And that would be totally okay if you did it that way. Just because we're in this new unit on work and energy, I thought I would avoid doing that. I'll show you how we can get the coefficient of friction using just this this newer physics, or maybe not just this newer physics, but leaning on it heavily. So here we go. The work done by friction is equal to the force of friction multiplied by the distance over which friction pushed it, multiplied by the cosine of the angle, beta, between the direction of the force of friction and the motion that's occurring. So this is just the work equation singling out what friction did. And I'll remind you that we know the work done by friction is this value, or even better, this value. Okay, so that means the work done by friction is force of friction mu times the normal force, and then the rest of the equation, distance friction cos beta. And of course, I've just explained how the normal force in this case is equal to mg, so I've subbed that in, which means that the work done by friction is mu mg distance friction cosine of beta for friction. I know everything in this equation except for the one thing I'm looking for, the coefficient. So solve for the coefficient, work equal to W over mgd cos beta, put the values in, and get an answer. By the way, notice that the beta value was 180 degrees because friction was pushing to the left while the motion was to the right. So there was 180 degrees between the force of friction and the motion. And that takes us to the end. So that definitely was a little bit quicker, although there were fewer problems in this set, so that also explains some of the time saved here. But again, if you prefer me solving the problems this way for the recording, let me know. If you think you're getting more out of me kind of solving them and you're actually seeing me writing up the solutions, I can do it that way. So hope to hear from you soon. Bye-bye.